Okay, so we are continuing with discussions on random processes. So let me erase this part also. So let's say this is part 2, second way of describing random processes. This is called moment description. Or moments, description by moments, okay? So what is this one? Okay. So again, I have a sample space. From this sample space, I'm generating functions, let's say. First realization. Let me have another color. A second realization, a random looking another function, x. Of course, they go for all t. It may be defined like that. Something like this. Let me have a third one and that will be it. Let's say that this is straight line like this, then it goes like this. Something like that. Now, what is PDF description? PDF description is this. Previously we have seen it. At a given time, let's say T1, you are trying to understand the distribution, the observed distribution at this time for this random process. If I have only 3 outcomes, you can say that, well, at this time I have this value and that value. I have only 2 possible values. Then the probability of having this is, let's say, 60%, this is 40%, that's it. That is the PDF description at time T1. As T1 changes, PDF description obviously changes because functions are taking different values. These outcomes are taking different values, as you see. There is also this joint PDF. If you have 2 time instance, now you are looking what is going on at T1 and T2 together. What kind of density do I have? So as we have seen, you can use factorization into conditional distributions to calculate such things, and so on. So this is previous knowledge. So what is moment description? Moment description is at time T1, I'm only calculating the first order moment, the mean value of this random variable. Okay. So first order moment description. Actually, we have seen this before. It won't be very surprising. This is expected value of, and this is called mean function, as we have seen before in Gaussian process. So this is just, of course, it is not the full PDF description. It is the mean value of this PDF. That is the reason that it's a partial description. Okay? But still, it has some importance. If I know the mean value, I can say something. Okay? Now the second order. For the second order case, in the PDF description, we had joint distributions. So guess what do we have over here? For the second order description, we may have autocorrelation function, expected value of x t1, t2. This is called autocorrelation function because I have 2 sampling instances and these are all moment descriptions, so there is some expectation going on. This is called autocorrelation function. Okay. There is also, of course, covariance function. So let me write it one more time. X of t1 minus, let me write this, introduce this mean function, mean value of t1 times x of t2 minus mean value of t2. Okay. So this is called, as in Gaussian distribution we have discussed this is called the covariance function. Obviously, covariance function is a function of 2 parameters because it's 2 random variables. It's related with 2 random variables. And this one is a function of a single variable, t. This is a function, it's the mean value of this distribution as t changes. Okay, that is it. So this is process variable t, and these are, random process realizations. So as you can imagine, calculation of these ones are a lot easier. But let me write a comment. Let me write comments. Number 1, calculation of moment description. Let's say first two, there can be higher order moments, but this is basically what we are going to do. First and the second order moment descriptions. Calculation of moment descriptions are much easier than joint PDF descriptions, obviously, because this is just a parameter, or not the parameter, but this is just the mean value of this PDF. Joint PDF description. And this is nothing but the covariance of two random variables. Okay? So it's not, a PDF. It's just derived from a joint PDF. Number 2, for Gaussian processes, first two moment descriptions, that is mean function, like we have written over here, and covariance function, is sufficient, as we have seen before, to write joint PDF description. For even nth order PDF, nth order, let's say, distributions. A few previous lectures we have seen this, okay? By expressing this function and this function, I can find, everything about this joint PDF by manipulating these parameters into the joint PDF expression for Gaussian processes. Let me write 3. In practice, PDF estimation is difficult, but moment estimation is much more easier, much more, let's say, practical. Okay? That means easier, actually. So this is the reason that we are, using this alternative moment-based description. This is basically calculation of these expectations, evaluation of these expectations by law of large numbers. You can use large number of experiments, Monte Carlo experiments, and you can do some time averages instead of these. This is called ensemble average. But we will discuss that later on. So this is just a comment for now. Well, that is it, I guess. Is there anything else? Where is the other paper? Of course, this should be for all t, not for a particular time. And these should be for all t1 and t2. Okay? Again, for all t1 and t2, not a particular unique time. This is a general description. Okay, now let me have an example related with this then. Okay. Okay, let x of t be a random process with mu x of t 3 and r x of t1 comma t2 is equal to 9 plus 4 e to the minus 0.2. There are some details, as you see. T1 minus T2. Okay? We have something like that. Okay, now we are defining a z random variable as x of 5. Where is this? W random variable. W random variable, these are definitions. This random process at the 8th time instant. So what are the questions? A. So not A. Find expected value of z, expected value of w, expected value of z square, expected value of w square, expected value of zw. Okay? Okay. A question like that. Our first example. So as you see, this is like an experimental conclusion. You see a random process, and this is described as, its mean is constant for all times, t, for mu x of t is equal to 3. Then its autocorrelation function is function of two parameters, two variables, as you see, given like that with that expression. So the question is find these expectation results from this information. So what is expected value of z? Well, this is expected value of x evaluated at 5, because this is the definition. Then, if I know the meaning of this, this is mu x of 5 is equal to 3. So what I see is that the random variable z, which is the evaluation of this random variable at the 5th time, 5th second, let's say, because this is t, let's say it's second, is, there is a density associated with that, but I don't know anything about the density, but it has a mean value of 3. Okay, that is it. That's all we know. Expected value of, there's a second variable, w. Well, this is mu x of 8, I guess. That is also equal to 3. Okay. So then expected value of z square. So what is z square? This is expected value of x5 times x5, let's say x5 times x5. Okay. Then this is equal to, by definition, autocorrelation function, Rx 5, 5. Then 9 plus, this is 1, 13. Okay. I get a result like that. Expected value of w square. So what's the purpose of this example? It has two purposes. Now we are seeing the meaning of this function, and how it is reflected in these calculations. And of course we see that we can only calculate these expectation results because I only know the moments, as you see. Okay, but it's still useful. I can get some information from these two functions, okay, about these z and the w random variables. So w is this. Let me write square over here. Rx 8, 8. This is also 13 because this is 0 or okay. Last one, z times w, expected value of. So these are the random quantities. So this is Rx 5, 8. So this is 9 plus 5 minus 8. 9 plus 4 minus 0.6. This is 3 in magnitude. Okay, I have that. So that is the end of this example. So what do we see? What do we see is that from this partial description, it's still valuable because for all T1 and T2 this is valid. I can write something about the means, variances, covariance of two random variables, etc. by processing this partial information. Right now they are functions of time, so for different times I can evaluate such results. Okay, which is good, somewhat useful. What else? Now let me have a second example. Let's say that you are implementing a kind of a linear time invariant filter on this random process. Actually, we will be doing that later on in much more detail, but our first example. Let's say that your filter evaluates the sum of two samples at time t1 and t2. Okay. So what is the question? Well, can we calculate, find expected value of z square? So this is like filtering operation. So this is like the power, you may say, output power after this operation. If these are the input samples, something like that. So whenever we see a second power, we interpret in electrical engineering like, this is a power dissipated over a resistor and so on. So this is the power of AC circuits, etc. Average power concept. Now how about the solution? The solution is expected value of, well, I can write, let's do not use matrices for this one. Not use matrices and vectors. Maybe we can do it that way also, but so this is expected value of this plus 2 expected value of T1, T2, expected value of T2, and I have something like that. So if I know, for example, moment description, I could have written Rx T1, T1 over here for this one. Okay, for this one, 2 times Rx T1, T2 plus Rx T2, T2. Okay, by definition. So as you see, this autocorrelation function, something like that, becomes important. If you can estimate this, maybe you can calculate this filtering output, let's say moments and etc. using this autocorrelation function and so on. Okay. This is, as you see, autocorrelation function immediately comes into play when you calculate these power quantities. What else? A third example. These are mini examples, as you see. Now S is equal to, from A to B, dt. Oh, okay. This is a little bit confusing looking, but, well, this is the reason I'm introducing this. If you apply our standard definitions, and if you apply our standard methods, we are done. This is a stochastic process, also called random process. So integration of random processes, well, it's actually quite tricky to explain formally, but let's do not formally explain this. At the end of this, if I am given a realization of this, this is the area calculation of this random process between times A and B. Okay, that is it. So what is expected value of S? So this is just a number. So what is the mean value of this number? Okay. I should say for a random variable, sorry, for a realization, this is just a number. If this is a random process, this is a random variable. What is the mean value of this random variable? Okay. How do I do this? So here is a trick. Now you insert this expectation inside of this integral. You always do similar tricks. You say that expectation of two things, they are summed up, a summation, distributes, well, it becomes a summation of two expectations. Okay. So this is integral version. So expectation can move inside. Then this is nothing but from A to B, mu x of t dt. So this is the area under, as you see, mean function. B, expected value of S square. So how can I calculate this one? Okay, let me write this. Expected value of S is equal to this, A, B, x of, let me write t1 over here, or let me write t over here, dt. And I should, this is S. I'm writing another bracket. This is also S, because t prime is just dummy variable. So one note, if you use t and t in both of these, there's a confusion. So after you do this product, of course, you should use something else for the second one. I'm using t prime because, after you multiply this, there will be a confusion. Okay, so this integration is over, this, random variable, random process between A and B. Okay, you can consider it like that. So how about this then? If I move, I have double integrals, A, B. So I move my expectation in. So this is expected value of x of t prime. As you see, it may look complicated, but the main idea is applying the definition and applying, the exchange of expectation and integration operations, like commutation of these two operations. So I have this one defined as Rx t comma t1, t prime. Okay? I have something like that. Then, so I see the following: A, B, Rx t comma t prime, dt, dt prime. Okay, I have this. Nothing new. Okay, very good. Now, these are somewhat practical results, you may say, if I know this moment descriptions, autocorrelation function, and so on. Let's have one more example. So this is an important example. Let me say x of t is equal to, well, this is A, random variable is A, cosine omega t plus theta. So A and theta are independent random variables. Okay. A theta is uniform in 0 to pi. Okay. A distribution not given. I don't know anything about this A distribution. Okay. Or PDF not given, let me say. PDF not given. So what's the question? The question is, okay, find mean function and Rx, T1, T2 autocorrelation function of this process. So previously we have studied, something very similar. But for that one, A was just a constant. It wasn't a random variable. Theta was again uniform in 0 to pi. And we have calculated the PDF description for this process. You may say that is a random phase sinusoid process previously. Now this is random amplitude and random phase sinusoid. Okay? So there can be frequency can also be random, but frequency is fixed for this example. Now let me calculate this one. Mu x of t. This is expected value of this. Then I have A. Oh, sorry. A is not constant anymore. A cosine omega t plus theta. Okay. I have something like that. Now I have, because of independence of these A and theta random variable, this separates into two parts. Okay. So this part is a function of one random variable, this is function of a second random variable, but this, they are independent, so I have such a result. So how about this one? This is mean of a random variable, whose PDF is not given. So I need to calculate this one. So how about that one? So this is, somewhat easy to calculate. This is a, so let me write, this is 0 to 2 pi. So uniform in 0 to 2 pi, 1 over 2 pi cosine omega t plus theta d theta. That is the second expectation. Okay. Well, whatever the value of this, let's say this is 5. I'm just making this up. You are integrating from theta is equal to 0. From 5 to 5 plus 2 pi. Now, what is the area of a cosine? So this is the cosine waveform. So this is, let's say, cosine x, okay? So it's periodic with 2 pi. What is the area under this cosine? Well, this area cancels this. This area cancels this. So under a full period, if you are integrating a cosine under a full period, it doesn't matter where you start. This is 5, let's say. This is 5 plus 2 pi. Okay? Of course, you can do an integration variable change, and it will change this. You can calculate this integral and so on. But at the end, you know, as an electrical engineer, we do this all the time. This cosine area under a cosine waveform over a full period is equal to 0, and then this is equal to 0. Oh, okay, very interesting. Then the mean of this random variable is equal to 0. Okay. Well, it doesn't matter what we have for a random variable. Okay. Now, autocorrelation function. By the way, this is a very important process in electrical engineering, because sometimes you observe signals with whose amplitudes are, because of this environment in communication channels and so on, amplitude is random, and phase of the signal is, in general, it is random, okay, in a communication system and so on. So this is a very practical, case, and of course you are tuned to a band, so this is the center frequency of that. Okay, maybe this is a narrow band process, etc. So on. Now how about this? Rx T1, T2. So what should I do? Now there is some simple calculation going on. Okay, random process. Correlation of two time instants are calculated. This is equal to expected value of a square this. Is this clear? Okay, just the definition. Now again, a random variable and theta random variables, they're independent, so this part is this, and this part is these two cosines. I don't want to write it one more time over here. Okay? So again, as an electrical engineer, what do we have? I have cosine A times B. So I remember this, let me check. As you can check this many ways, this formula, but you have to make sure that it is correct. For example, when B is equal to 0, this cosine A on the left side, okay, it matches, that is a good thing. If A is equal to B, 2 cosine square A minus 1 is A plus B cosine 2A. I think this is correct, okay? If it matches such sanity checks, it has to be correct because of my earlier experience. I can prove this if you wish using Fourier transforms and so on, but that's good enough. Or, well, as a signal processing engineer, let's say, assume that this is 2 pi f0t, this is 2 pi f(a)t, this is f(bt). If you multiply these two, what do you have? You have in the Fourier transform, you have a shift from fa plus b, and you have a shift from a minus b. So I should have things like that on the right side. You have 1 over 2s, etc. and so on. This is how you remember things. Okay. Now, if I do this, then expected value of a square, and in the bracket, then I have such a case where a is equal to this. So let me move this 1 over 2 out of this bracket. Then this is expected value of cosine A plus B, this and this. Where's cosine? Sorry. cosine omega t1 plus t2 plus 2 theta. So this is my a plus b, a, b, plus expected value of cosine a minus b okay, and there is a parenthesis over there. Is this correct? There is a product distributes into a sum, converted into a sum, and I have something like this. So this is a minus b. Okay, now I have to calculate this expectation. What is the random quantity over here? Theta. So what's the, wow, very interesting. There is no random quantity inside of this argument. So there is nothing random anymore because a minus b thetas cancel, as you see. So I can move this out of this expectation immediately. There is nothing to do. How about this one? Well, let's say that one more time. This is equal to 5. So if that is equal to 5, so it is exactly the same calculation. But this is 2 theta. What does it make a difference? I have a 2 theta over here. So I'm integrating over 2 full periods. Because if you run from 5, it goes from 5 to 4 pi. Okay? Because at the end, you have 2 theta, 5 plus 4 pi. You are covering the area over 2 full periods. Okay? So that is also equal to 0. So that part is also equal to 0. So what do I get? I get expected value of a square over 2, and this is cosine omega t1 minus t2. Okay? So this becomes Rx t1 comma t2. Okay? So that is the end of this problem. But, well, this is actually very important result for us. We will discuss this later on. But just a fact. Notice that right-hand side is a function of, let's say, delta. Let's say t2 minus t1. Okay? So time difference between 2 time instances. Okay? Obviously. Because it's just a constant. This is, for example, that is, if you have Rx t1 plus, sorry, not plus, t1 plus delta. Okay? This is always equal to Rx some other time, t1 prime plus, t1 prime plus delta. Because in this case, this is t2, this is t2, and you see that the difference of these 2 parameters are affecting this calculation. And their difference is always delta. So what we see is that now this right-hand side can be defined as a function of this time difference, delta. So this will be important later on. Okay? We will be discussing such things. This is just an observation for now. That is it. Now, what else? I want to discuss. Let me see, where is the eraser? But let me postpone this discussion. But let me have it in the next lecture. Let me give some, notes. If we have complex valued processes, such as x of t is equal to a e to the j omega t plus theta. Let's say that it's almost like the same, something like this. Then, of course, mu x of t definition is the same, expected value of x of t. but our x of t definition, t1 comma t2. So whenever you have complex quantities, there is always a change, because you will see immediately. I have something like that. So let me, actually this is the important part that I want to say. Second argument conjugated. So this is has a conjugate. This is the definition. Well, the reason is, when these two arguments are the same, I want this thing to be not parentheses square but magnitude square. Okay? Because if you have complex numbers, parentheses square of complex numbers is another complex number. But I want magnitude square, because this will be something like, it will be, if it's zero mean, it will be the variance of that random variable. So this random variable and this random variable, let's say this is z conjugate. If z is zero mean, then z magnitude square, expected value, will be the variance. By definition, it will be the variance of it. So just because of it, and because of this inner product, considerations and so on, I want to have, over here. Of course, you could have put this second, instead of the second argument conjugated, I could have put the first one. But in this course and in many textbooks and so on, this is always the second case. So let's use it that way. Now, if you are concerned, then we have these definitions. So these are the definitions for complex valued random processes. Of course, if you know the definition for complex valued random process, this is more general. If it is real valued, this conjugate doesn't do anything. Okay? So this is maybe more fundamental definition for our purposes. So then let me have this. So same as previous example, same conditions for A and theta, okay, as in previous example, this one that we have solved. So the goal is find, so let me define one more time this, x of t is equal to a e to the j omega t plus theta, and find mu x of t and rx t1 comma t2. Okay. So let me try to finish this a little faster. What is the mean value of this? Well, the mean value is expected value of A times expected value of e to the j omega t plus theta. Okay? J is multiplying both of them. Okay? I have this. Is this okay? So how about this? This is cosine Euler's formula plus theta j sine omega t plus theta, and again this is 5, let's say. So both cosine and sine, they are periodic with 2 pi, and I'm integrating over a full period. So this is 0 plus j0 after expectation. So this is 0, then the result is 0. Now let me try to do this. Expected value of Rx so let me find the autocorrelation function for this complex valued process. But since this is, as you see, complex valued, let me have conjugate over here. So this is part B. This is equal to then expected value of A square. This is expected value of e to the j omega t1 plus theta times e to the minus j omega t1 plus theta Is this clear? Because now x1 at t2 is conjugated. So there's a minus sign over here. Okay. So what do I have? So this is T2, right? This is T2. This is J omega T1 minus T2. So random variable again cancels out. J theta minus J theta. They cancel out when you sum the exponents. Okay, so there is nothing random anymore inside of this expectation. So I get expected value of T1 minus T2. So this is just our delta as before. Okay, so this is Rx T1 comma T2. Okay, so as you see, with complex exponentials, I don't need to use these trigonometric formulas. I don't even need to remember them, as you see. This is the power of, you may say, Euler's theorem. And this is the power of, phasor definitions, etc. in electrical engineering. Okay, that's all for today's lectures. So we will continue with more discussions later on.